It's Mr. Dave with the National Museum of Nuclear Science and History. Welcome to Nuclear Science Week. And we are here in the museum, and we have another fun little demonstration or simulation for you guys to do today. This one is based off of a thought project that involved some of the things I have here at the table, along with, let's see, this guy in here. We do have a cute little kitty cat. Yes, this cute little kitty cat. This one was actually made by my daughter. I said, hey, I'm going to do that Schrödinger thing, and she said, let me make you a cat. And so she made me this little bitty cat, and this will be our cute little kitty for our Schrödinger's demonstration. Okay, if you would like to come up with a name for this cat, you can put it down in the comments below. It currently doesn't have a name, so we have to come up with a name for this cat. So we've got this cute little kitty, and it will be part of our demonstration when we're talking about a thought process that Schrödinger came up with to kind of describe and conceptualize some of our heavy quantum things and all of these scientific concepts. Okay, now the idea behind this whole process is that we have got radioactive decay. Okay, now we do have another video that you guys can watch. If you're following along here, there is one that is what is a half-life. So there is another video you guys can watch that it will be linked to this one, and we'll kind of expand on this one, and that one's got some activities you can do also. In ours, we are going to be doing the Schrödinger's cat, or in our case, Schrödinger's spider, and I'll show you why in just a minute. So with our Schrödinger's cat, the idea for this thought experiment was if you had an atom, a single atom of nitrogen 13, N13. N13, the half-life of that is about 10 minutes. Okay, so that means that in that 10-minute span, it may or may not decay. Okay, so like I say, if you want to learn a little bit about half-lives, hit that other video called What is a Half-Life? And we will take you through a fun experiment on determining a half-life. All right, so let's get into this kind of thought experiment. If you had nitrogen 13, N13, and this will represent our N13, okay? If you had that N13, which we decided in a matter of 10 minutes may or may not decay, okay? It's got a relatively short half-life, 10 minutes. Now, when we are talking half-lives, sometimes they're fractions of a second, sometimes they are thousands of years. All right, so if we have our N13, which this here is actually americium, it's a little bit different. This is something from a smoke detector, but we're going to use it as that example. Now we have our Geiger counter here. This one is the TBM3S contamination meter, and this is what is going to be detecting that radiation. Now, when you hear those little beeps, those little blips, that is when something is undergoing radioactive decay. It puts off radiation, and it can be in different forms, but we're just going to go into when it decays, it will emit a type of radiation, okay, alpha, beta, gamma. And so we're going to turn our little Geiger counter on here. You'll hear that beeping sound. That means it is detecting radiation in the area around us. Okay. Now, there's always that background radiation, but we're going to see if it can detect the radiation from this little guy here. And you see when we put it up there, whoo, terrible amount of noise coming from that thing, right? So we get a lot of radiation from this little guy here. So this is going to kind of, in our thought process, we're going to imagine that this is our N13, okay? So we've got our Geiger counter. We've got our N13, and these are the things that Schrödinger kind of proposed to determine if something has in fact decayed or has not, or how do we know? And so what we're going to do is we're going to kind of emulate that scenario. And so we have our Schrödinger's cat. Remember, we still need a name for this cute little guy. But we're going to put him in the box. Okay, so we're going to put the cat in the box. So we already have the cat in the box. So the next thing we're going to have a hammer. Now, we're not going to hit the cat with the box. This particular thought experiment was maybe even a little bit scarier because we have a poisonous gas inside of this bottle here. Now, it's not actually a poisonous gas. We're just imagining, okay? So we're going to put our poisonous gas in here. And you notice the bottle is glass. And so we are going to have our hammer, which can break the glass, okay? Now remember, this is going to detect whether our nitrogen 13 does decay in that 10 minutes or does not. Now, it's a real 50-50 chance, and I say that because I want you guys to kind of think about probability. 50-50 means there's the exact same amount of chance that it does happen, that it doesn't. Now, there's a lot of different probabilities and things that can go into this particular experiment, and that's the point, is because you really just don't know. So you won't know if this has decayed or not. Now, the reason that's important is because we're going to put it in the box with the cat. Okay. Now, the radiation from this is not going to kill the cat. We're talking, our imagination is that there is one single atom of that N13. Okay, so it's going to have one emission if it does decay. Okay, so there's one single atom. Now, of course, this has a lot more. You heard those beeps. That's a lot of atoms decaying. But one little beep would mean that one atom did decay. Now, we're not going to be able to hear it because we're going to put it in this soundproof box. Okay, but what we're going to do is we're going to put our emitter. Okay, this is our imagination. This is going to be our N13. We're going to put it inside of our device here. Now, this device here is going to hold our N13 in addition to swinging our hammer. Okay, so I'm going to put this in here, and what's going to happen is when we hook up our Geiger counter to our device, okay, so now we have our Geiger counter that will be hooked into our device here that will swing the hammer only if that atom decays. Okay, so if that atom decays, it's going to swing this hammer. Now don't worry, we're not going to hit the cat. We're actually going to unleash the poisonous gas. So we're going to put the hammer in here. We're going to hook it up this way. Now, if that atom decays, if that one N13 atom does decay, then our Geiger counter is now going to tell our device to smash our glass bottle, exposing the cat to the poisonous gas, and it will die instantly. Now, that's pretty gruesome, right? But remember, that one N13 atom may or may not decay in that time. So there is actually a very deep quantum explanation, but whether we're going to know if this cat is in fact dead or alive. So at any point after I start this, okay, I'm going to close the box. I'm going to lock the box. Okay. Our timer has started. Our cat is now in the box. At any point in time, that atom could decay. If that atom decays, the Geiger counter is going to detect that. It is going to cause our device to swing the hammer and essentially poison the cat. So as of right now, is that cat dead or is that cat alive? Yeah, I don't know either. And that was the point of this experiment. At any time, this cat, to my knowledge, is dead and alive. Oh, no, wait. To my knowledge, it would be dead or alive? That is what this thought experiment proved, was there is no way to me of knowing, which means where I am, this cat right now is both dead and alive, or it's neither dead or alive. So while we have our cat waiting in the box here, we're going to talk about something that you can do at home, because I really would not recommend taking little furry animals, putting them in boxes with poison and hammers. So what we're going to do is we've got kind of a way of just visualizing this experiment at home that's a lot cheaper, and one that you can do with just a couple things you get at the dollar store. So what we have here is I've got a little bitty tin. Now what's important about this is that you cannot see into it. Okay, it wouldn't work to use like Tupperware or something like that, because you can see through that and you'd be able to see the result. Now, our cat is still in there waiting, so we're going to go ahead and show you what I have in here. I have little bitty toy spiders. Okay, so I've got a bunch of little bitty toy spiders. Now remember, we're talking that one N13 atom, so that would be one little spider. Okay, now I'm going to double that, and I'm going to use 2. And the reason we're going to do that for our little example here is because we want to see that it really is something that is random. And so, or as close to random as we know, or as we can achieve. So I'm going to put my little spiders in my little container. So for this one here, the way we're going to determine whether these spiders are in fact dead or alive, in this case, is if your little spider is standing on its little feet, then it will be alive. If the spider is on its back, then we're going to count it as dead. So remember that when you open up that jar to see whether your little spiders are dead or alive. All right, here we go. And I'm going to shake it up. Okay, now I recommend for this one that you use plastic spiders, because real spiders are going to be very angry when you go to take them out of the container. So we've got the 2 in here, and what we're going to do is we're going to label them. Our little green one, our little glowing one, will be spider A, and our little black one will be spider B. Okay, so we've got spider A and spider B. We're imagining that both of those are those nitrogen-13 isotopes or atoms. Okay, so I'm going to open my container, and I'm going to see whether these spiders are alive, or whether these spiders are dead, or because we have 2 of them, we have a third option. That would be one of them to be alive and the other one dead. Now with our cat in here, we have the same situation going on. Right now, this cat, for all intents and purposes, is dead and alive. Okay, and it's neither dead or alive. So we've got the same thing going on with these spiders, but we're going to find out which is going to solve that problem, because we will now know whether they are dead or alive. So here we go. We're going to open up with our little spiders and see how we do. Oh, now what we have here is I do have one spider that remained alive. Our little bitty green spider here, our spider A, did remain alive. So one of those atoms did not decay. Our other spider, however, yeah, it didn't make it. So one of those nitrogen atoms did decay, one of them did not. Now, what this is showing is giving us a little, let's try it again and see what happens. Okay, yeah, this one didn't bode well for the spiders. I think both of our nitrogen atoms decayed. Our little spider B did, well, he's gone now. Spider A, also gone. So we saw in that one that both of those atoms did decay, even though it was that same shaking thing. It's kind of like rolling a dice. Now this is something that you can do with Scrabble tiles, with coins, and we do actually have another video that you can watch on Half-Life that will extend this part of the demonstration a little bit for you, and you can actually determine the half-life using a whole bunch, because when you use more than just 2 or 1, your probability changes, and you will get a more accurate determination of the half-life of something. So we're going to give this one more shot before we check out to see whether our cat is in fact dead or alive. Well, we got one. Our little, this time, our spider B is still alive. Yay, spider B! And spider A, spider A did not make it. So you can see we're getting different results every time, and that is because of that probability, and that is that question that was posed by Schrödinger to the scientific community and even to himself on how do we determine this thing that on a quantum level is still pretty random. So let's check in on our cat Remember, we don't have a name for our cat yet, so if you want to name our cat, you can put that in the comments. We're going to see how our kitty did. Okay, we're at the end of our imagined 10 minutes. We have our little kitty in there. I'm kind of scared to open the box, because what if the cat is not alive? I am a cat person. I do have a cat at home, and so it would be sad for me to open this box and the little kitty be gone. So here we go. Ready? I'm gonna open the box. It hasn't attacked me, so I don't know if that's a good sign or not. Oh, hey, our little cat, our little kitty. Our little kitty is still alive. Our little kitty did survive. It did in fact survive our little thought demonstration here. So in this case, that means that little atom did not decay. Okay, that little atom survived this round, this 10 minutes, that half-life, and was okay. And that means our Schrödinger's cat is all right. So let's give our little Schrödinger's cat a big hand. There you go. And thank you guys for joining us for Nuclear Science Week. If you want to know a little bit more about half-lives, check out that half-life video. We have some demonstrations, some hands-on stuff you guys can do at home with that one. And as I say at the end of every video and everything I ever do, don't forget to wash your hands.